In the summer of 1964, deep inside Ford's engineering offices in Dearborn, Michigan, there was a problem nobody wanted to admit out loud. Chrysler's legendary Hemi was becoming untouchable. On drag strips, on NASCAR ovals, and in pure bench racing conversations across America, the 426 Hemi had become the monster everyone feared. It made a factory-rated 425 horsepower and 490 pound-feet of torque. But most insiders knew those numbers were a lie. Real output was closer to 500 horsepower in race trim. Some dyno operators whispered numbers even higher. It inhaled air through massive hemispherical combustion chambers and giant valves that looked more like industrial machinery than car parts. The thing was a phenomenon. Chrysler had cracked the code on high-performance breathing, and every other manufacturer knew it. Ford needed a response. And what happened next created one of the strangest engines in American history. Because Ford built an engine that, on paper, was actually better than the Hemi. More airflow, higher RPM potential, more top-end horsepower, bigger ports, bigger ambition, better flow bench numbers than almost anything Detroit had ever conceived. But then it disappeared. Most people have never even heard its name. The Ford 427 tunnel port. And the reason it vanished says everything about the brutal reality of American racing in the 1960s. About the difference between engineering ambition and racing survival. About what happens when you push too far, too fast. By 1964, the horsepower war had become a full-scale arms race. Chevrolet had the mysterious 427 Z11 program running in secret back rooms. Chrysler unleashed the Hemi on an unsuspecting public. Pontiac and Oldsmobile were pushing compression ratios so high that premium fuel barely survived detonation. Engines were grenading on test stands. Engineers were calculating power outputs that would have seemed impossible just 5 years earlier. And Ford? Ford was desperate to dominate everywhere at once. NASCAR, NHRA, Le Mans, Daytona, Pikes Peak, Bonneville. The company was spending millions chasing Ferrari in Europe while simultaneously fighting Chrysler on American soil. Corporate pride was on the line. Market share hung in the balance. Racing on Sunday, selling on Monday wasn't just a slogan. It was survival. But there was a major problem hiding inside Ford's FE big block engine family. The standard 427 side oiler was brutally strong, genuinely bulletproof in most applications. With a 4.23-inch bore and a 3.78-inch stroke, it displaced exactly 427 cubic inches. The famous side oiler oiling system fed the crankshaft first, solving the bearing failures that destroyed earlier high RPM FE engines. Oil pressure stayed consistent even when the engine screamed. In race trim, the side oiler could survive 7,000 RPM for hours. Days even. That's how Ford won Le Mans in 1966. Endurance, reliability, power. But Chrysler's Hemi was starting to outrun it, especially at high RPM, especially where pure horsepower mattered most. The Hemi's giant cross-flow cylinder heads moved insane amounts of air. That meant more fuel, more combustion, more power, more wins. At Daytona and on drag strips across America, Ford engineers realized something terrifying. Their engine had reached its airflow limit. The FE architecture, as strong as it was, simply couldn't breathe like the Hemi. The intake ports were smaller. The valve angles weren't optimal. The combustion chambers were conventional. Efficient, yes, but not revolutionary. And then the real nightmare started. Ford engineer Moses Mose Nowland later described the atmosphere as pure panic. The company needed an emergency solution. Not in 5 years. Not in 2 years. Immediately. NASCAR seasons didn't wait for development cycles. Drag racers weren't going to park their Plymouths while Ford caught up. The competition was brutal and relentless. So Ford's engineering team decided to do something radical. Instead of redesigning the entire engine from scratch like Chrysler did with the Hemi, they tried to turn the existing FE block into an airflow monster. Take the proven bottom end, the bulletproof side oiler system, the forged internals, and bolt-on cylinder heads so extreme they would make the Hemi look conservative. The result looked insane. The intake ports on the new cylinder heads were so huge that the push rods literally passed directly through the center of the intake ports inside steel tubes. The push rod actually traveled through the intake runner, through the path where air and fuel were supposed to flow at maximum velocity. That's where the name came from. Tunnel port. Imagine air entering the intake runner at full speed while the pushrod sat inside a metal tube right through the middle like a tunnel running through a highway. It looked ridiculous. It looked like something a backyard mechanic would sketch on a napkin and an engineer would immediately dismiss. But on the flow bench, it worked. And the numbers were terrifying. The tunnel port heads flowed over 400 cubic feet per minute on the intake side in race form. That was enormous for the 1960s. That was numbers nobody had seen outside experimental programs. Some NASCAR teams claimed the engine could pull cleanly beyond 8,000 RPM with the right valve train setup. With the right components and tuning, some insiders whispered about 8,500 RPM. That was Hemi territory, maybe even beyond it. Most people don't realize how extreme this engine really was. The intake valves measured a gigantic 2.25 inches. Exhaust valves were 1.73 inches. To put that in perspective, those were dimensions you'd expect on much larger displacement engines. Compression ratios climbed past 12.51 in race trim. Some radical builds went even higher. Detonation became a constant threat. Fuel quality was critical. Most dyno tests reportedly showed over 550 horsepower naturally aspirated with dual 4-barrel carburetors. Some claimed even more. In an era when 300 horsepower terrified normal drivers, when insurance companies were already starting to panic about muscle cars. But there was a problem. Actually, several. The giant intake ports that made incredible top-end horsepower also killed low-speed velocity. Basic physics. Airflow volume was massive, but airspeed dropped dramatically at lower RPM. That meant weak throttle response and poor torque below racing speeds. The engine needed RPM to wake up. Lots of RPM. On paper, the tunnel port beat the Hemi. In the real world, things got complicated. At NASCAR tracks in 1967, Ford teams started testing the engine aggressively. Money poured into development. Drivers immediately noticed something strange. Below 4,000 RPM, the engine felt lazy, soft, almost dead. Throttle response was disappointing. Then suddenly, around 5,000 RPM, it exploded to life like a switch had been flipped. Like something fundamental changed inside the combustion process. One mechanic reportedly described it as driving into a tornado. The engine made unbelievable top-end power. The kind of power that slammed you back into the seat. But keeping it in the power band became difficult, especially on shorter tracks. Tracks with tight corners, tracks where you couldn't stay at 6,000 RPM constantly. And reliability? That became another story entirely. At sustained RPM, valve springs began failing violently. The giant valves created enormous mass in the valve train. More mass than the available spring technology could properly control. Push rods flexed under the loads. Rocker arms cracked at stress points. Lifters collapsed. Teams found metal shavings glittering inside oil pans after races. Little fragments of destroyed components floating in otherwise clean oil. Mechanic Herb Knabb allegedly told one Ford team owner, "It sounded fast right until it scattered itself across the racetrack." But Ford kept pushing, because the stakes were enormous. Because admitting defeat to Chrysler wasn't an option. Not politically, not financially, not in the culture of 1960s Detroit. At the 1967 Daytona 500, the tunnel port entered the biggest stage in American stock car racing. Ford desperately wanted to humiliate Chrysler's Hemi in public, in front of television cameras, in front of the national media. That race mattered politically inside Detroit almost as much as financially. Bragging rights for an entire year hung on that single event. And for a moment, it looked possible. The tunnel port engines were unbelievably fast in qualifying. Tiny Lund and Mario Andretti both showed incredible speed during testing sessions. The engines screamed down Daytona's banking at nearly 190 miles per hour, inhaling air through gigantic ports that sounded more like aircraft engines than stock cars. The sound alone intimidated competitors. Then came race day, and things started breaking. Oil temperatures climbed beyond safe ranges. Valve float appeared at sustained RPM. Several engines developed ignition issues from the violent harmonics at high speed. Spark timing became unstable. Drivers complained the engines became unpredictable late in runs. Power would surge, then fade, then surge again. Meanwhile, the Hemis just kept pounding laps. Steady, brutal, reliable. Lap after lap after lap. And that was Chrysler's secret advantage. The Hemi wasn't just powerful. It was manageable. It didn't require perfect conditions. It didn't demand constant attention. It worked. The combustion chamber design created efficient airflow without requiring absurd port dimensions. Chrysler's engineers had found balance, the sweet spot between maximum power and real-world reliability. Ford's tunnel port had gone all in on maximum airflow, and the compromise was becoming painfully obvious. You could see it in the results sheets. You could hear it in the pits. But Ford wasn't done yet, because drag racing changed everything. On NHRA strips, where engines lived at full throttle and maximum RPM for only seconds at a time, the tunnel port suddenly became terrifying. The reliability issues mattered less. The narrow power band became manageable with proper gearing. Lightweight Fairlanes and Mustangs equipped with tunnel port 427s started posting quarter-mile times deep into the 11-second range at over 125 miles per hour. Some combinations cracked into the 10s. That was elite territory in the late 1960s. And racers loved the violence of the power delivery. When the tach swept past 6,000 RPM, the engine came alive with a screaming fury few American V8s could match. It didn't feel like traditional torque. It felt explosive, violent. Drivers said it felt less like torque and more like an avalanche of horsepower crashing all at once. One racer reportedly joked, "Below 5,000 RPM, it's asleep. Above 5,000, it's trying to kill you." For quarter-mile racing, that personality was perfect. You can probably guess what happened next. Ford engineers tried fixing the weaknesses. They experimented with revised camshaft profiles to improve low-end drivability, different lobe profiles, different lift and duration numbers. They tested smaller intake cross-sections. They upgraded valve train components with stronger springs and revised geometry. Exotic materials appeared. Titanium retainers, improved metallurgy. Some NASCAR teams even altered gearing ratios just to keep the engine inside its narrow power band. But every fix created another compromise. Smaller ports reduced the monster airflow advantage. The whole reason the engine existed. Softer cam timing hurt peak horsepower. The dyno numbers dropped. Stronger springs increased friction and heat. Oil temperatures climbed even higher. And then the timing turned catastrophic. In 1968, NASCAR introduced rule changes that shifted the entire battlefield. Regulations that favored different engine characteristics. At the same time, Ford was developing a completely different solution behind closed doors. A cleaner answer to the Hemi problem. The Boss 429. And suddenly, the tunnel port became yesterday's experiment. An expensive lesson. A stepping stone. The Boss 429 solved many of the same problems with a cleaner design. Semi-hemispherical combustion chambers. Better breathing efficiency without the compromises. More stable valve train geometry. Huge canted valves. It was Ford's true answer to the Hemi, the solution they should have built from the beginning. The tunnel port had become a stepping stone, a very expensive stepping stone. Only a tiny number of production tunnel port engines were ever built. Estimates vary wildly, but most historians believe fewer than 100 complete street-oriented tunnel port cars left Ford factories. Some estimates place total engine production around only a few hundred units, including race programs. Compared to the thousands of Hemis Chrysler built, that's almost nothing. And the cost was staggering. A complete 427 tunnel port setup could cost nearly double what lesser FE engines cost at the time. Specialized parts, exotic head castings, race-only maintenance schedules. It simply wasn't practical for ordinary buyers. Insurance companies wouldn't touch them. Dealers didn't want to service them. Meanwhile, insurance companies were beginning to attack muscle cars aggressively. Premiums exploded overnight. Young buyers couldn't afford coverage. Emissions regulations loomed on the horizon. The federal government was watching Detroit. The golden age of unrestricted American horsepower was starting to collapse. And the tunnel port became one of its first casualties. But here's the crazy part. Even though the tunnel port failed commercially, even though it disappeared almost immediately, many racers still believed it had more raw potential than the Hemi. On pure airflow numbers, it absolutely competed. Some measurements showed it superior. Some modern engine builders who restore tunnel ports claim the original design was simply ahead of available technology. Better valve springs, modern metallurgy, improved fuel delivery systems, and modern camshaft design solve many of the issues that destroyed reliability in the 1960s. Computer-designed cam profiles, fuel injection, modern ignition systems. In other words, Ford may have accidentally built a future engine decades too early. An engine that needed 1990s technology to reach its full potential in the 1960s. Today, genuine tunnel port parts are almost mythical. Original heads can sell for tens of thousands of dollars at specialty auctions. Authentic intake manifolds are collector treasures. Real factory tunnel port cars appear at auctions so rarely that some enthusiasts spend decades searching for one. Entire online communities exist just to track surviving examples, because they represent something special, not perfection, but ambition. The tunnel port was what happened when engineers stopped caring about moderation and chased maximum airflow at any cost. It was Detroit operating without fear, without restraint, without accountants stepping into the room and demanding profit projections. Pure engineering ambition unleashed, and honestly, that's why people still love it. At modern vintage racing events, restored tunnel port engines still scream at terrifying RPM. The sound is unforgettable, sharper than a Hemi, angrier than most big block Chevys. It almost sounds mechanical in an unnatural way, like the engine is inhaling the atmosphere itself, like something industrial that escaped the factory. And when people hear it, they stop. They turn their heads, because they know they're listening to something rare, something that wasn't supposed to survive, something that failed commercially but succeeded as legend. The Hemi became the legend. It won championships. It dominated headlines. It stayed in production long enough to build an empire around its name. Generations know the Hemi brand. The tunnel port didn't. It burned bright, burned hard, then vanished. But maybe that's what makes the story so fascinating, because sometimes the most important machines aren't the ones that win forever. Sometimes they're the wild experiments that pushed engineering right to the edge of disaster. The machines that asked what if, without worrying about the answer. The Ford 427 tunnel port beat the Hemi where engineers cared most, on airflow charts, dyno sheets, and raw racing potential. But racing isn't won on paper. It's won with reliability, balance, and survival under pressure. It's won by finishing races, not just leading them. And that's the brutal lesson hidden inside this forgotten engine story. The lesson about the difference between peak performance and consistent performance, between theoretical superiority and practical victory, between what works on a flow bench and what works on Sunday afternoon with 100,000 people watching. Ford learned it the hard way. If you enjoyed this deep dive into forgotten racing history, let me know in the comments what engine or rivalry you want to see next. Should we talk about Chrysler's Wild Max Wedge program? The mystery behind Chevrolet's aluminum ZL1 427? The insanity of Pontiac's Super Duty engines? And make sure to subscribe so you don't miss the next piece of forgotten racing history, because there are dozens of these stories. Engines that should have dominated, technologies that appeared too early, racing programs that burned millions and vanished. The 1960s were full of them. And most people have never heard the real stories behind the legends.